The AI said the network was stable. One engineer disagreed. Minutes later, the system nearly failed, not because the AI malfunctioned, but because it optimized the wrong thing. For years, the industry has promised fully autonomous networks powered by artificial intelligence, self-healing systems, predictive automation, infrastructure that runs itself faster than any human team ever could. And in many ways, that future has already arrived. AI can detect anomalies, reroute traffic, predict outages, and automate network decisions in real time. But one overlooked anomaly exposed a dangerous truth. AI can process millions of signals instantly without truly understanding what matters most inside the system. And that's why the future of networking may depend less on replacing humans and more on keeping humans in control. Modern enterprise networks are too complex for humans to manage manually, including cloud computing, remote work, IoT devices, edge computing, AI workloads, all creating constant pressure on infrastructure teams. A single enterprise network can generate millions of telemetry events every hour. Packet loss, route changes, DNS failures, authentication requests, traffic spikes. Human engineers simply cannot monitor all of it in real time anymore. And sometimes, this system making those decisions are changing routing behavior thousands of times per second without direct human review. Most users never notice. Until a tiny optimization error spreads faster than engineers can react. That's why companies began deploying AI-driven networking systems. These platforms use machine learning trained on historical traffic patterns to predict outages, detect anomalies, automate routing decisions, optimize bandwidth usage, and identify security threats. AI is now deeply embedded into modern infrastructure, and for many organizations, automation is no longer optional. It's survival. But one invisible weakness inside these systems is making engineers increasingly nervous. AI doesn't understand intent, it understands patterns. Modern AI networking systems operate using massive streams of telemetry data. They analyze latency, packet flow behavior, CPU utilization, link saturation, device health metrics, and traffic anomalies. Then compare them against learned patterns. If congestion appears likely, the AI reroutes traffic before bottlenecks occur. If packet drops increase, it isolates affected segments automatically. Some systems even detect attacks like traffic patterns faster than human analysts. In many cases, AI performs better than humans at scale because machines never get tired and they don't miss data. But networks don't fail only because of obvious signals. Sometimes they fail because of relationships between events AI was never trained to understand. Humans excel at contextual reasoning. Experienced engineers detect patterns that look meaningless in isolation but dangerous when connected. This is why infrastructure is shifting towards hybrid intelligence. AI handles scale, humans handle judgment. AI processes millions of signals, humans interpret consequences. AI systems are becoming like autopilot for the internet, incredible during normal conditions, dangerous if nobody is watching the cockpit. And the difference between these two abilities may decide whether systems stay stable or collapse silently. In one enterprise environment, an AI optimization system managed traffic across multiple data centers. It continuously adjusted routing based on latency and bandwidth efficiencies. For months, everything improved. Fewer outages, faster load balancing, less manual intervention. Engineers began trusting the automation almost completely. Then something changed. During a routine traffic surge, tiny latency fluctuations appeared between two regional clusters, barely visible. Less than a few milliseconds. The AI classified it as normal adaptive congestion. No alert triggered, no alarms fired, no thresholds exceeded. CPU usage looked normal. Packet loss remained low. Average latency barely shifted. But one engineer noticed something different. The pattern resembled early-stage route instability he had seen years earlier, involving BGP path recalculation conflicts. Individually, nothing looked wrong. But together, the signals formed a pattern consistent with a cascading routing failure. He manually paused the automation system. Minutes later, investigators discovered a routing policy update had propagated unevenly between regions, creating conflicting BGP path preferences across multiple edge clusters. The AI optimized locally, but the human saw system-wide risk. Had automation continued aggressively, it could have triggered cascading failure across multiple services. And this exposed a core limitation of AI systems. They are excellent at pattern recognition, but weak at understanding ambiguity outside their training boundaries, which changes everything about the role of engineers. They are no longer just operators, they are supervisors of intelligent systems. There is a dangerous assumption growing in tech that once AI becomes accurate enough, humans are no longer needed. But highly autonomous systems introduce a new risk: silent failure. When humans stop questioning automation, errors compound invisibly, and the most dangerous failures are the ones nobody investigates, because everything still looks normal. AI does not understand responsibilities. It doesn't understand consequences, business impact, ethical trade-offs, and long-term system stability. It follows objectives, and if those objectives are misaligned, optimization itself becomes dangerous. An AI optimizing efficiency during instability may continuously reroute traffic, correct in logic, but destructive in outcome. Humans recognize when stability matters more than efficiency. That distinction is critical. AI may operate the network, but humans define the boundaries it operates within. Over the next decade, networks will become increasingly autonomous. Outages predicted before they occur. threats dictated in real time, systems self-optimizing continuously. But paradoxically, this will increase demand for high-level engineers because failures inside autonomous systems will become harder to detect, not easier. New roles are already emerging: AI network supervisors, infrastructure automation architects, AI systems auditors, and human-machine operation specialists. The future won't belong to those competing with AI. It will belong to those who govern it. One engineer caught what the AI couldn't, and it revealed something bigger than a system failure. AI can process information faster than humans ever will, but humans still understand context, responsibilities, and consequences. The real risk was never loud failure. It was silent failure, hidden in systems everyone assumed were stable. Subscribe for more real-world AI investigations where systems dictate the signal and humans uncover the truth.